Has started.
Okay, so technical difficulties behind us. Hopefully we can get rolling now. There are a few problems I want to have you guys try before we move on to new material this morning. First one looks like this. That is a half circle. The diameter across here is 4 foot 6 inches. I want you to find the distance around that circle. Or that half circle, I should say. Think of it as if we're putting an edge around it. How long would that edge have to be? And the second one I'm going to have you do, again, find the distance around or find the perimeter on this. This is a rectangle. This is going to be 3 feet 8 inches by 5 feet 3 inches. So I'll give you a couple minutes to work on those, and we'll go over them in just a little bit. Let's take a look and see how you're doing. So this first one, finding the distance around it involves part of the circumference of a circle. Remember, we talked about circumference is equal to the diameter of the circle times that mystical pi. Well, pi is a scalar number like what we were looking at the other day with our operations. However, using that, it's a decimal scalar number. It's not a whole number. So multiplying a dual unit like 4 feet 6 inches by that would be really tricky to do. It could be done, but it's just not going to be pleasant. So it might be easier for us to convert this all into inches first. So remember, we had mentioned you can treat it like a mixed number. Think of this as 4/12 of a foot. And just like with a mixed number, we do 4 times 12 is 48. Add 48 to the 6, that's 54/12 of a foot, or just 54 inches that 4 foot 6 inches is equivalent to. So 4 times 12 made 48 inches, plus the 6 was 54 inches. So we have a diameter of 54 inches. And now to find the circumference of a circle, it's going to be 54 times pi. Now you can either use your pi key or you can just use 3.14. I'm just going to use 3.14 here. That complete circle would have a circumference of 169.56 inches. But this is not a complete circle. It's only half a circle. So I have to divide that by 2. 84.78 inches. So that is the part that I have traced out in brown there, but we want the distance around the whole thing. We still need this piece across here, that diameter. So we're going to have to add that 54 inches back into it, which gives us 138.78 inches. So that's the distance around that whole piece. If you came up with that, you answered what I had asked you to do here. But now, before we move on to the second problem, let's do a little bit extra. Let's change that into feet and inches to the nearest 16th of an inch. So I have my 138.78 inches. To change that into feet, the first thing I need to do is divide it by 12. Or I could multiply by 1 over 12, 1 foot over 12 inches, which is technically what I'm doing. But let's just divide by, oops, I gotta add my 54 there first. I'm going to divide that by 12 to get feet. That is 11.565 feet. Well, all I want off of that is the 11. There's 11 feet there. How many inches are left? Well, I'm going to take off that 11 feet. I have 0.565 feet left. Well, I'm just going to multiply by 12. Turns that part back into inches. That's 6.78 inches. Let's review what I did there. I started out with 138.78 inches. Turn it into feet, I divided by 12, which gave me the 11.656. Then I took off the feet, the 11 whole feet, I subtracted those to leave me with just the decimal portion of the feet left, and I converted those back into inches by multiplying by 12. Get me back to the 6.78. Now I need to take that 6.78 inches and give it to the 16th of an inch. So I'm going to subtract the 6 off of that. I have 0.78 inches right now. If I look at 0.78 is a fraction, it's 0.78 over 1. So to turn that into 16ths, I'm just going to multiply by 16 over 16. So 0.78 times 16 is 12.48, which is slightly closer to 12 than it is to 13. So that's 12 sixteenths, or 3/4 of an inch. So this is 11 feet, 6, and the 0.78 is 3/4 of an inch, to the nearest 16th of an inch. Now you might say, well, why'd you go 3/4 when it said to the nearest 16th? Well, 3/4 is still 12 sixteenths. It's just been simplified. So that is still to the nearest 16th inch. On a quiz, if you got to this point, I'd be more than happy with that. Number 2 here, I put out here because this is one that we can work with the dual units. If you wanted to convert it all into inches and then convert it back later, you could. That would work. A couple ways I could go about this. I could double each of these first and then add them together, or I can add them together and then double them. I'm going to take the shorter route. I'm going to add them together first, and then we're going to double them because there's the other sides. So 3'8" plus 5'3". 8 plus 3 is 11 inches. less than 12, so I don't have to carry. 3 plus 5 is 8 feet. So I now have 8 foot 11 inches. I need to multiply that by 2 because there's 2 more sides of those same lengths. 11 times 2 is 22 inches. That is 1 foot and 10 inches. So we keep the 10 inches. Carry the 1 foot. 2 times 8 is 16, plus 1 is 17 feet. So that is 17 feet, 10 inches. Any questions on those? Okay. There are problems on your quiz that are very, very similar to those two. There's also one on your quiz. Can't remember what problem number it is. Let's see if I don't have the quiz up anymore, do I? That is mislabeled. It says like 15 inches, 7 inches. That should be 15 feet, 7 inches, or whatever. I just hit the wrong key. It's a typo on it. Be aware of that. And then also on the quiz, there's 2 problems where you asked to measure. You asked to measure the length of a line, and you're asked to measure the diameter of a circle. Of course, you guys know how to use a ruler. Just lay the 0 at one end and read where the other end is. For a circle, you put the 0 at one side of the circle, and you kind of move the ruler back and forth until you find where it's the longest dimension for the diameter of the circle. If you're doing those on a computer screen, you're going to be limited to the scale of your computer screen, and I totally understand that. My answer key is designed, if you print it off, it should always come out to the same size printed. So if you have the ability to print that quiz, that'll help you answer those 2 questions. If you don't, just make a note for those 2 questions that you measured on the computer screen, and I will, compensate for that when I grade it. Does anybody have any questions off of the homework from yesterday? Okay. Well, then we'll get moving on here today. We talked about operations with our length units yesterday. Today we're going to move to talking about area units. And our area units are nothing more than a combination of our length units. It's the product of 2 length units. So our most common area units that we work with in the standard system are square inches. And square feet. Sometimes pronounced just inches squared, which is the way it's abbreviated, or feet squared. A square inch, of course, is just a square that's 1 inch by 1 inch. Square foot, this will not be drawn to scale, but is just a square that is 1 foot by 1 foot. Now remember, a simple linear inch length unit, an inch is just a length that's 1 inch long. A foot, again, not drawn to scale, just 1 foot long. Those dimensions, an inch and a foot, are one-dimensional. They're only a length. They're along a line. For our area units, however, they're 2-dimensional. Because they are 2-dimensional, our conversion factors will not hold. Let me show you what I mean by that. Let's do a rectangle here that is 2 feet wide and 3 feet long. The area would be 3 feet times 2 feet, or 6 square feet. But if I convert those into inches, 2 feet is 24 inches, and 3 feet is 36 inches. If I find the area in inches, it is 36 inches times 24 inches, which ends up being 864 square inches, or inches squared. Now, if we look at that, our linear conversions definitely don't hold. You can't take, to turn feet into inches, we multiplied by 12, but you don't do 6 times 12 is 72. That is nowhere near 864. So how do we get from that 8 square feet into square inches? Well, the way we do it is we have to remember that this is square feet, not linear feet. And square feet is feet times feet. If I go to convert that, put it over 1. If I use a conversion factor where there's feet on bottom and inches on top, 1 foot is 12 inches. This is only going to cancel out one of those feet, not both of them. Remember square feet being feet times feet. I either have to use this conversion factor twice, so there's feet on bottom to cancel out twice, so it cancels out both of them, or I have to use a conversion factor with the squared units built in. In fact, I get that conversion factor from these 2 linear conversion factors. I had to use that factor twice. The conversion factor for the area units, the squared units, is the square of the linear conversion factor. 12 inches over 1 foot, if I square that, well, 12 squared is 144. Inches squared is inches squared. 1 squared is 1. Feet squared is feet squared. There is 144 square inches in 1 square foot. If you sketch that out, it actually makes sense. Because a square foot was 1 foot by 1 foot, which would be 12 inches by 12 inches. Well, 12 inches times 12 inches is 144 square inches. The 1 square foot is equivalent to 144 square inches. So our conversion factor up here to change 6 square feet into square inches, rather than having to use the linear conversion factor twice, we can just use 1 square foot equals 144 square inches. So now the square feet cancel out. I have 6 times 144, which does give us that 864 square inches. It's 864 square inches over 1, which is just 864 square inches. So our conversion factors with our square units are not the same as our linear conversion factors. They come from them, but they are the square of those linear conversion factors. So if I have 5 square feet of material, and I need to know how many square inches that is, take my 5 square feet over 1, square feet on bottom so they cancel out, and 1 square foot is 12 squared, or 144 square inches. So the square feet will cancel. 5 times 144 is 720. Nothing times inches squared is inches squared. On bottom, 1 times 1 is 1. So that is 720 square inches. Or if I want to go the other direction, if I have 3,456 square inches, and I need to know how many square feet is that. That's one that would be a lot simpler if it was expressed in square feet. Oh, I'll take my 3,456 Square inches, put them over 1. And my conversion factor, now square inches have to go on bottom, so the square feet will be on top. 1 square foot is still 144 square inches. Square inches cancel out. 3,456 times 1 square foot is 3,456 square feet. On bottom, 1 times 144 is 144. And now we have to divide that out. Excuse me. I believe that comes out to 24 square feet. 3,456 divided by 144 is 24 square feet. So 3,456 square inches is only 24 square feet. So you can see those numbers seem way different size. But again, because it's an area unit, because it's a squared unit, those conversion factors are squared, and the numbers shrink very quickly if you go to a larger unit, or get large very quickly if you go to a smaller unit. Only 5 square feet was 720 square inches. And over 3,456 square inches became only 24 square feet. So we can use that with our other units. Let's say we want to look at, let's say we have something that is 81 square feet. And I need to convert that to square yards of material. This is a unit that gets used a lot in the tailoring industry, fabric and clothing. More everyday application is going to occur more with the cubic units or volume units of cubic feet to cubic yards, but we'll get to that at some point here soon. So 81 square feet into square yards, we have to know what the conversion factor is for square feet to square yards. So you start out with the larger unit, which is the yards, and you think of a square yard as 1 yard by 1 yard. Well, 1 yard is 3 feet. So that's 3 feet by 3 feet. So the area of that is 3 feet times 3 feet, or 9 square feet. So 1 square yard equals 9 square feet. It's just the 3-foot linear conversion factor squared. So I have my 81 square feet. I'll put it over 1. Square feet on bottom, so they cancel out. Well, 9 square feet equals 1 square yard. So square feet cancel out. 81 times 1 yard squared is 81 square yards. And 1 times 9 is 9, and we divide that out. 81 divided by 9 is 9 square yards. So 81 square feet is only 9 yards. Well, we can work with some of our lesser known units. We might have four square rods. Let's convert that into square yards. Well, again, 1 rod by 1 rod is a square yard, or square rod. So 1 rod is 5.5 yards. So a square rod is 5.5 yards by 5.5 yards. If we multiply that out, 5.5 yards times 5.5 yards, what is that? 30.25 square yards. So 1 rod is 30.25 square yards. 1 rod squared, I should say, is 30.25 square yards. So I have 4 square rods. Put it over 1. Put square rods on bottom here. 1 square rod is 30.25 square yards. The square rods cancel out. 4 times 30.25 is 121 square yards. 1 times 1 is 1, so that's just 121 square yards. Now, square rods does not get used much, but a square chain does. We didn't talk about this unit. We mentioned it briefly when we talked about length units, but we didn't do anything with it. One chain is 4 rods. That's not terribly useful to us, though. We know 4 rods. Let's convert that into feet. We know that 1 rod is 16.5 or 16.5 feet. The rods will cancel out. 4 times 16.5 is 66 feet. 1 chain is 66 feet. Well, why is that important? Well, let's look at what a square chain would be. One chain by 1 chain will be 66 feet by 66 feet. So that means that's going to be 66 feet times 66 feet, which gives 4,356. Square feet. That is a very important unit when it comes to land surveying and land measurement. The unit that we are most used to hearing land measured in is the acre. Well, 1 acre is 43,560 square feet. Look at that number, and you look at this one here, you see a relationship. Technically, 1 acre, the origin of 1 acre is it was 10 square chains. So be very, very careful when you are trying to convert units with area units, if it's squared units. Let's take a peek here at area in general, rather than just the units. Area of a rectangle. We will talk about these way more later on in the course, but for now we're just going to use the formulas. Area of a rectangle is just length times width. Kind of used that already when we talked about our square units. So if this is 4 feet by 11 feet, that area, 11 feet is a length times 4 feet of a width, gives us 44 square feet. If I wanted that in square inches, remember 1 square foot is 144 square inches. So that'd be 44 times 144. 6,336 square inches. Now, there's nothing there that I didn't tell you to find it in square inches. Once we got the 44 square feet, I just wanted to do a conversion to practice those conversions. Triangles. We're looking at right triangles especially. Area of a triangle is base times height divided by 2, or 1/2 times base times height. Either way you look at it. So let's say that this is 6 inches tall. and 24 inches long. That area is 1/2 times 6 times 24. Of course, those are inches, which gives us 72 inches squared. If you wanted to practice turning that into square feet, you could. It actually comes up to be 1/2 of a square foot. There's something called a trapezoid. For your program and machining, you're going to use a ton of formulas, so you just will get used to applying some formulas here. A trapezoid is a four-sided figure with one set of parallel sides. Redraw this side down here to make it look a little bit closer to parallel. That looks a little better. The two sides that are parallel in this figure, the top and the bottom, are called bases. Notice I spelled one of them with a small b and one of them with a large b. So I'm going to refer to the top one as little b and the bottom one as big B as the bases. The distance between those bases is the height, or sometimes referred to the width. So for a trapezoid, the area is the average of the bases, little b plus big B divided by 2, times the height. So if I put in some numbers here, let's make this 22 inches. Down here, we'll make this 8 inches, and we'll make this height here 16 inches. So this is going to be 22 plus 38 divided by 2 times 16. So at this point, once we put the numbers into our formula, it's just an order of operations problem now. 22 plus 38 is, what is that, 60? Then we have to do the 60 divided by 2, which is 30. Now the parentheses are down to a single number, so I can get rid of them. And 30 times 16 is 480. Those were in inches, so that unit will be square inches. If I needed to know square feet, I would do 480 square inches over 1. Square inches on bottom is 144 square inches in 1 square foot. Square inches cancel out. I've got 480 square feet over 144. I divide that out. 480 divided by 144. 3.33 square feet, or 3 1/3 square feet. And of course, the area of a circle there we talked about the circumference of a circle being the diameter times pi, or pi times diameter. For area, it's pi times the square of the radius. Again, at some point when we do areas more formally, we'll come back and we'll look at where that formula comes from. But for right now, let's say we have a circle with a diameter. Well, let's do a diameter of 32 inches. That's the diameter. So the radius is half the diameter. So that's going to be 32 inches divided by 2. Giving us 16 inches is the radius. So our area will be pi times 16 squared. .14 times 16 squared. Here's 803.84. Square inches. Seems like a huge number, but if we convert that into square feet, Put the 803.84 over 1 square inches on bottom here. 144 square inches is 1 square foot. Square inches cancel out. 803.84 times 1 square foot is 883.84 square feet. On bottom, 1 times 144 is 144. And we divide that out. 803.84 divided by 144. We get only 5.582 square feet is all that is. So when you list something in square inches, you get this number that makes it seem like it's huge, but it really isn't. I realize I'm a few minutes past our break here, but we'll get to it in just a minute. One application of area that is very important is pressure. More importantly for us is the pressure to force relationship. Our formula for pressure is equal to force divided by the area it is spread out over. So if I have 400 pounds of force spread out over 16 square inches, excuse me, my pressure is the 400 pounds of force divided by 16 square inches, which comes out to be 25. But I also divide the units. Pounds divided by square inches is pounds per square inch. Gives me a pressure of 25 pounds per square inch. So if I have a hydraulic ram, and let's say this hydraulic ram, yeah, I know, that's a pretty ugly drawing, but you guys get the picture, is a 4-inch diameter ram, assuming standard circular. So the area of this plate on the ram is the area of a 4-inch diameter circle. That means it has a radius of 2 inches. So the area is pi times 2 squared, which comes out to be 12.56 square inches. Well, let's say that we have a pump, hydraulic pump here, that's capable of producing 400 psi, which is pounds per square inch of force. The force can be thought of, if I rearrange that pressure formula, as the pressure times the area. So I can take my 400 psi, come on, 400 pounds per square inch, times 12.56 square inches. And you'll notice here the units even work out. The per square inch and the times the square inch cancel out. 12.56 times 400 is 5,024 pounds. So about 2.5 tons of force are produced by that small ram. Okay, with that, we'll wrap up the first hour here. We'll give you your homework. Your homework is 2 parts here. In the big book, we have page 296, exercise 8-5, 7 through 29, the odd. And page 297, exercise 8-6, 7 through 13 the odd. Then in the little book, unit 30 the odds. Okay, it is now almost 8:29. Let's come back at 8:39 and we'll pick up from there. Okay, it's that time, so let's get rolling here. For our second hour here, I want to talk about a couple of things. First is metric units. Let's start out with our metric units of length first. We're calling it our major unit of length is the meter. And as we went either direction, let's go smaller first. We have the decimeter, that's 1/10 of a meter, centimeter, that's 1/100th of a meter, millimeter, that's 1,000th of a meter. Going to the right, we have a decameter, which is 10 meters, a hectometer, which is 100 meters, and a kilometer, which is 1,000 meters. Now, we did have other units if we kept going, but they skipped spots. On the small side, we skipped 2 spots. And we hit micrometers, which is a millionth of a meter. On the large side, we also skipped 2 spots. We skipped the 10,000 and 100,000. Went up to megameter, which is a million meters. And for length, each of those positions on the chart was multiplying or dividing by 10. So each position on the chart was just moving the decimal point one spot. If I had let's do 28,000 millimeters converted into meters, I'm going from millimeters to meters. That's 1, 2, 3 spots to the left on the chart. My decimal point, since there isn't one written, it's at the end of the number here, has to go 3 spots to the left. That turns into 28 meters. Or if I had 0.79 meters and I wanted to turn it into centimeters, here I'm going from meters to centimeters. That's 1, 2 spots to the right on the chart. My decimal point here has to move 1, 2 spots to the right. 0.79 meters is 79 centimeters. Because every unit, every step on that chart is multiplying or dividing by 10, we can just move the decimal points to convert units in our metric lengths. Any of our metric units, to be honest, as we hit them. For metric area, remember with our standard area, it was the length conversion factor squared. Well, for metric lengths, that conversion factor is always 10. So if we square a 10, we get 100. So if this is now meters squared and decimeters squared and centimeters squared and millimeters squared, or decameters squared, hectometers squared, and kilometers squared, if that's the case, then each spot on the chart is multiplying or dividing by 100. And when we multiply or divide by 100, it just moves the decimal point 2 spots. So if I have now 28,000 millimeters squared instead of just millimeters, and I'm going to meters squared, well, from millimeters to meters is still just 3 spots to the left on the chart, but now each of those spots is 2 decimal places. So 3 spots on the chart is 6 decimal places in our number. So our decimal starts at the end again. We go 1, 2, 3, 4, 5, and we have to add a 0 to go 6. That's 0.028 square meters. If I have my 0.79 square meters, and I'm converting to square centimeters or centimeters squared. Again, on my chart from meters to centimeters is 1, 2 spots to the right, but each of those spots is 2 decimal places. So 2 spots is 4 decimal places. So I take my decimal and I go 4 spots to the right. I go 1, 2, then I have to add 2 zeros to go 3 and 4. 0.79 meters squared is 7,900 centimeters squared. So when we're doing conversions on a quiz, possibly Tuesday, you have to be very careful. Is it millimeters to meters, or is it millimeters squared to meters squared? Because that squared means you've got to double the number of decimal places you have to move. So let's do some examples here. I have 520 millimeters squared to centimeters squared. On my chart, from millimeters to centimeters is 1 spot to the left. But these are squared. So I have to go 2 decimal places for that one spot. So I have to go 1, 2, that is 5.2 centimeters. If I have 0.63 centimeters going to millimeters, from centimeters to millimeters is one spot to the right on the chart. And this is just centimeters and millimeters, so it's just one decimal place. If I go over one spot, that's 6.3. Had it been 0.63 centimeters squared to millimeters squared, that's still centimeters to millimeters is still just one spot to the right on the chart, but because it's squared, that one spot would have been 2 decimal places. 0.63 centimeters squared would be 63 millimeters squared. So you have to be very, very careful with our metric method when doing those conversions. Now I want to talk a little bit more about area and calculating area. Threw out some formulas there. I don't like doing that without showing where they come from. So I'm going to step back here for the rest of our time and talk about some basic geometry. Just like we talked about how in arithmetic, everything is built from that concept of a number, and the number having 2 parts, the count and the name. In geometry, everything is built from one concept as well, and that is that thing right there. It's called a point. It is just a location. It has 0 dimensions. Because if you're on that point, you cannot move in any direction. There's 0 directions you can move without leaving the point. Sounds very simple, sounds kind of useless, but that point is what builds everything that we use in geometry. If I take that point and I move it, I drag it across the surface, kind of like an Etch-a-Sketch. You move it across, it leaves its trail. Or think of a point of a stick in the sand. It leaves its trail across the sand. What I have created there, often referred to as a line, technically it's a line segment. Technically a line goes on forever in both directions. Well, in practical applications, that's not very useful. So we will typically refer to it as a line, but technically it's a line segment. The length of that line is equal to the distance that the point was moved. This is now one dimension. Because if I'm on that line, I can move one direction without leaving the line. Now you might say, well, I can move this way or I can move this way. It's like, yes, but that's just the positive and negative of the same direction. So then I can take that line segment and I can move it in a second direction. Again, think of a stick laying on the sand and you're pulling it across the sand. It traces out its path as you move. The key is this direction has to be what we call perpendicular to the original. Perpendicular means at a right angle, but a little bit more powerful than that. It means at a right angle in every measurable direction. Well, on a flat surface, there's only measurable in one direction. What we have created here is an area. And technically, it's a rectangle. Or a rectangular area, if you want to call it that. The size of this area depends on the length of that original line segment, and again, the distance moved. That distance moved, though, now is usually referred to as a width, so that we can distinguish it from that original length. This is now two-dimensional. Two dimensions. Because if I'm in the rectangle, I can move in two directions. I can move side to side, or I can move up and down, and I stay within the rectangle. Now you might say, well, I can move this way. Isn't that a separate direction? No, it really isn't. If I am moving that way, I'm really moving in components of two directions, horizontal and vertical. There's only two components of that movement. You could also think of the two dimensions as being, it took movements in two different directions to create that object. So this is what brings us to that formula that area is equal to the original length of the line times the distance moved, or the width. Now the neat thing about that area, well, let's just do a rectangle here quick. Let's do an example. Let's say that this is 8 inches by 15 inches. That area will be a length of 15 inches times a width of 8 inches. 15 times 8 is 120. Inches times inches is inches squared. We know being an area, it has to be a unit squared. Well, that's a rectangle, which means we moved perpendicular. But the interesting part is we don't have to move perpendicular as long as that original line segment stays in its same orientation. I take my 15-inch segment here, and I move it. Notice it's staying, so it's not twisting or anything, it's staying parallel to its original orientation. Let's say I move it at an angle like this. So those corners are not perpendicular. But the distance from where I started to where I stopped is still 8 inches. If we look at this, if I were to cut this into really thin slices, really thin little rectangles, each of those rectangles is going to be 15 inches long. And the total height of those rectangles stacked up is going to be 8 inches. So if I just take and I push on those rectangles and straighten them up, what I would get is this rectangle up here. Those rectangles would just be perfectly stacked straight up and create a 15-inch by 8-inch rectangle. So the area of this is called a parallelogram. Is the same as the area of that rectangle. It is the distance between where that line segment started and where it ended that matters. So the area here is still that 15-inch original segment times the distance moved of 8 inches for 120 inches squared. In fact, it doesn't even have to move in a straight line. If I take my 15-inch original segment here, let's say I move it in some crazy pattern like this. Trace out the edges, of course. As long as it stayed parallel to its original orientation, and as long as the distance it moved from where it started to where it stopped is still 8 inches, the area of that is still 15 inches by 8 inches, or 120 inches squared. And again, the reasoning is I can think of this as being really thinly sliced rectangles that fill this in, each of those rectangles is going to be 15 inches long, and the total width is going to add up to 8 inches. So it would still fill up that 15 by 8 rectangle that we had up top. These little rectangles, by the way, these little green rectangles I drew in, that's basically the theory of calculus. Now, we're not calculating anything here. We're not going to do any calculus in here. That's really how calculus works, is you're taking shapes, at least the analytical geometry portion of calculus works, is you're taking these shapes and you're cutting them into thin enough slices that you can approximate them with rectangles and then add those rectangles together. Now, there's a lot more to it to make the math work on how we do that, because the strategies for cutting things up and then the strategies for adding them all together so you don't have to write out thousands of little area rectangles is complex. But that's the basic idea of calculus, is you cut things down, if you slice things thin enough, everything becomes a rectangle. In fact, in math, a rectangle is the only shape that we know how to calculate the area of. You might say, well, but we just saw formulas for a triangle. Well, let's look at a triangle here. Let's look at a right triangle. This is 8 inches by 15 inches. Well, this triangle has what we refer to as a related rectangle, which means it's really viewed as part of that rectangle. I assume that looks like right angles. I got a little slanted there. But it's part of that original rectangle. In fact, we can see that it's exactly half of that rectangle. So the area of a triangle is length times width, the area of the related rectangle divided by 2. So here it's going to be 15 inches times 8 inches divided by 2, or 60 square inches. It doesn't have to be a right triangle. It just has to fit into the same related rectangle. So I have a 15-inch base. And it goes like that. So I need this related rectangle that fits around it like this. So I know the 15 inches is the length of that rectangle. I need to know this width or height of that rectangle. Well, from the triangle, the dimension of that triangle that gives us that width is the distance from this opposite corner or opposite vertex back to that base that we knew, the 15 inches, measured at a right angle. That's what that little red box means there. It's a square. It's a square corner, a right angle. This is what's called an altitude or a height of our triangle. If that is 8 inches, guess what? The area of this triangle still has a related rectangle of 15 inches by 8 inches. And the triangle is half that, so divided by 2, it's still 60 square inches. Where it's a little more difficult to see is if the triangle doesn't stack up straight like that. Let's say we have 15 inches here, and our triangle slants off like this. That's not as easy to see. But let's draw out actually 2 related rectangles. Now, if I go up here, this one actually came from 2 related rectangles as well. I have one here, that portion is half of that rectangle, and one over here, this portion is half of that rectangle, which shows us that's half of that related rectangle. This one's a little trickier. This triangle in blue is part of a bigger triangle, which would be this one in purple. If I took the purple triangle and I subtracted this green piece here, I would get the blue triangle. Well, the same is true then for the related rectangles. If I took this dark brown rectangle and I subtracted the green one, I would get that tan rectangle. So that's kind of the justification for saying that that triangle is still half of this related tan rectangle. So the distance, the height of that rectangle is still the distance from this opposite corner, opposite vertex, back to that base, only it still has to be measured at a right angle or perpendicular. So we have to extend the base up. What's that?
Are you on your section of the screen? Because I don't think we can see what you're working on.
Oh, my screen froze up again, didn't it? Okay, give me just a second here. There we go. Does that look better?
Yeah.
Okay, so this height here, get back, is still 8 inches. I realize you guys couldn't see the explanation there, but this black triangle is still half of that related tan rectangle because I can chop it into pieces and make it fit. So the area of this would still be just 15 inches by 8 inches for the related tan rectangle, divided by 2 because that triangle is half of it. Then we have that trapezoid. Trapezoid's actually simpler than you might think. We have the two bases that are parallel. They're connected, of course, with non-parallel sides. Let's say that this base up here is, well, let's just say it's 12 inches. Let's get the distance between bases here. We'll call that 20 inches. And this base down here, we're going to call 30, let's call it 32 inches. To turn that into a rectangle, what I would do is I would go halfway down one of these sloped sides. Let's go right there. I'm going to chop this off square here. If I flip this little corner up, it should fill this in exactly. I just squared off one edge of that trapezoid. I do the same on the other side. I go halfway down, chop this off square. I can flip that up to fill that in. So that rectangle I have is now related to the trapezoid. The width of the rectangle is still just that 20 inches, that height of the trapezoid. The length of the rectangle is between the two bases, the 12 inches and the 32. In fact, it's exactly between. It is the average of those bases. 12 inches plus 32 inches divided by 2. Well, 12 plus 32 is 44, divided by 2 would be 22 inches. So the area for a trapezoid, if little b is the short base and big B is the large base, is the average of those bases. That gives us the length of that related rectangle times the height. So the area of this would be 12 plus 32 over 2 times the height of 20. So 12 plus 32 is 44. 44 divided by 2 is 22. Don't need the parentheses anymore. 22 times 20 is 440 square inches. Let's look at circles. So we know that for a circle, of course, the diameter is 2 times the radius, or the radius is half the diameter. We know the circumference is pi times the diameter, or 2 times pi times the radius, because 2 times the radius equals the diameter. And we've seen already, we know that the area is pi times radius squared. But I had mentioned that every area, the only area we really know how to calculate is a rectangle. And every area comes from a related rectangle. So how the heck do we turn a circle into a related rectangle? Well, it comes back to that idea of calculus again and thin slices, but not how you might think. So let's take this circle and we're going to cut it in half. Now we know, this circle has a radius of r. We know that the distance around this circle, the whole circumference, is 2 times pi times r. So that means for this half circle, we divide that by 2, it would just cancel out the 2. That distance around is pi times r. Just half of that. So what I'm going to do is I'm going to take that half circle, I'm going to cut it into really thin pie wedges, basically, pie slices. Then I'm going to fan those slices out. It's going to look something like this. Looks almost like a sharp tooth comb. The distance across here, if I cut those slices thin enough, is just this half of the circumference, pi times the radius. This distance here is just the radius. Now if I take the other half of the circle and I cut it in equally thin slices, pie wedges, and I fan those out, and I slide that comb into this other one, they should fit perfectly. If I cut them thin enough, what I get is a rectangle that has a length of pi times radius and a width of the radius. If I multiply those together, I get pi times radius squared. So that's where that formula for the area of a circle comes from. It does come from a related rectangle. So if I have a circle, the diameter of 10 inches, to find the area, pi times 5 squared. Where did that 5 come from? The 10 inches we gave you was the diameter. Area is pi times radius squared. So we had to take half of the 10 inches to get a radius of 5 inches. So pi times 5 squared, 78.5 square inches. In the big book, page 320 is exercise 9-5, 7 through 21 the odd. And page 321 is exercise 9-7. Once again, 7 through 21 the odd. Also, there is a quiz out there for today, labeled September 18th, that is due at noon on Monday.
What were those last couple book pages? Because
It froze up again, sorry. Let me get back to it here. I don't know why I'm going to have to shut everything down here. And there we go. Do you see them better now?
Yep.
Okay. I'm going to have to shut everything down here before my next class and see if I can't get a better connection. This is frustrating. Sorry about the troubles today. Yeah, so remember, there is a quiz out there for today that is due by noon on Monday. Make sure Okay, with that, if you guys don't want to stick around and work, I feel like with all the frustration with the technical difficulties, I don't blame